Today on Applied Science, I'd like to show you an unusual property of rubber bands and also demonstrate a mechanism that I built that makes use of this property. So here's what you can do. You can try this at home. Just go to your office drawer and pick out a couple of regular rubber bands. The bigger the better. This one is a size 64. And what you want to do is stretch it really hard and then hold it up to your lips. So let's switch to thermal vision so that you can see what I feel. And so here's the rubber band, and it's kind of at room temperature. The scale here is about 27C to 34C. Now if I stretch it really hard, you can see that the rubber band actually warmed up. And if I hold it to my lips like this, it's warm. I can feel it. It's quite noticeable change. So you might be thinking, well, that's not that exciting. I mean, it's probably just friction in the rubber, car tires heat up and all this. However, if you keep the rubber band stretched like this and either blow on it or just hold it out in the air for a while and then let it contract, watch what happens. It actually gets colder than room temperature. And if I put it back up to my lips, it's noticeably cold. So when you try this, stretch it really hard so you get a good difference. And then, like I say, blow on it a little bit so that it comes back down to room temperature. And when you let it contract, it's definitely cold. What a weird property, right? So I'll let you think about why it does this. At first, it might seem counterintuitive because if you know, gases get cold when they expand and get hot when you compress them, it almost seems like the rubber band is doing it in reverse, where when it expands out, it's getting hot. And when I let it contract again, it gets cold. So we'll talk about this at the end of the video, but right now I wanted to show you a mechanism that I built that makes use of this property. If you search around on the internet, you'll see an unusual device that looks like a bicycle wheel that's made out of rubber bands. Basically, the rubber bands take the place of the spokes. And if you shine a light, like a tungsten light, on one side of the wheel, the rubber bands will change shape and cause the wheel to become off-center, and it will roll around, exposing fresh rubber bands to the light bulb. So you might be getting the idea here that rubber bands can act as kind of a part of a heat engine, just like the refrigerant does in your refrigerator. So I searched around to see if anyone's tried building an actual refrigerator from rubber bands, and I couldn't find anything. So I decided that would be a great thing to give a shot. I used the same idea of having a wheel with an offset hub so that half the rubber bands would be stretched and the other half would be in their natural state. And then we know that the stretched half is going to be hot, so we want to have that outside the box, and then the contracted state will be inside the box, and with some fans to kind of blow the hot air off of the hot ones, and another fan to blow the cold air off the cold ones. And if you put the wheel kind of right on the edge of the boundary of the box, this whole system can work. And I know the sealing is not going to be that great, of course, but really it's just a demonstrator just to see if this thing can work at all. I did most of the modeling in SolidWorks and exported all of the flat faces as SVG files, and then used my handheld CNC router made by Shaper to cut all these pieces out. So I've actually been looking for, to do a lot of projects out of wood like this that would require a wood router, and I don't have one. But this CNC handheld router is really the best way to do it. And if you're watching this video in August 2016, you're in luck. These are actually available for pre-order now. And I think the price is going to be under $1,500 if you're quick. So go to Shaper Tools, and I'll put a link in the description if you're interested in this. Unlike a laser cutter, one thing that's nice about having a router is that you don't have to cut all the way through the material. Like, you can make a pocket very easily. So if you just want to core away some material, it can do that. And also, this is kind of thick for a laser cutter, so I don't really know if you'd want to do 1/2-inch thick plywood. It leaves the edge unburned, which is another nice thing. And so for all these reasons, this really is the best tool to make wood box type things with the joinery and everything. I created the gears using a free SolidWorks gear creation tool, and the fit is actually even better than I would have guessed. The gears actually work really well. Okay, so let's see this thing in action. Of course, I'm using the thermal camera again so that you can see the parts heating up and getting cold as they're moving. And as you might guess, it's not like it's going to cool your beer down or anything like that. I mean, it's, barely a temperature change, but you can actually see it pretty clearly on the thermal camera. The stretch of the rubber bands is a little too much, so when I was prototyping this, I had a little jig on the table, and I was checking to see where I could reliably stretch the rubber band and how much temperature change it actually created. It's about 2 degrees C for the stretch that I was putting into it. And it's getting near the limits of what those rubber bands can take. I actually thought I had a bit more margin than I do. But as you can see, a lot of rubber bands have snapped, and partially that's because of the wood breaking, and partially that's because of the rubber band snapping. But anyway, this thing could use a redesign, and so next time I'll let you know if it's in better shape. I ran it with the door closed for just a little while, literally just 5 minutes or something like that. And you can just barely perceive that it's slightly cooler inside than it is outside. Although I admit this might just be because I'm standing near the thing and just my body heat might be warming up the outside. So it might look like it's just getting cooler inside, even though it's the outside that's warming up. So coming back to these rubber bands, the actual reason that they get cool when you let them contract demonstrates an interesting law of thermodynamics. So think about this. If you have like an aerosol paint can and you spray some paint out, the can gets cold because the gas expanded. And everyone, intuitively knows that that's fine, but the rubber bands appear to work in reverse, where when they contract, they get cold. So it almost seems like it's sort of breaking the law. But it's actually the same thing, and here's how to think about it. When you spray some paint out of the can, think about why the gas even wants to come out of there, right? Like, you've opened the nozzle. There's no physical reason that air couldn't rush inside the can and make the pressure even higher, but it's favorable for the universe to sort of equalize disorder. And so when you press the nozzle, because the pressure is higher inside, it wants to equalize with the pressure outside, and that's what drives this whole process. So what's strange about the rubber band is that when it's in the contracted state, all the molecules inside there are actually very tangled up. And when you stretch it, you're actually making it more ordered. You're actually putting the molecules more straightened out. So the stretched version of the rubber band is much like the compressed gas in the can, because you've done work to sort of segregate those molecules and putting them inside the can. So if you sort of take your hands off the system, you're not applying any work or you're not controlling it, the universe tends toward disorder, entropy basically. And that's what causes this thermodynamic thing to happen. It's the reason that the rubber band wants to return to its shape, and it's also the reason that as it contracts, it's doing work and it's getting cold. So this is an entropy-driven process, which is actually the same as a gas. It just has sort of an opposite appearing effect. Okay, well, I hope you enjoyed that, and I will see you next time. Bye.